guys, welcome to lecture 1, probability and stats. This first lecture is going to be an introduction to random variables. So, first I just want you guys to just think about the definition of these two terms, probability and statistics. What is statistics? Is a statistic the mean, the mode? Those are our statistics. What's the field? And how is it different from probability? Think about those yourselves. You can pause the video. Think about that for a second. There's no wrong answer. And then we'll go on to the third question, right, which is probability and stats boring? Think about that, but there's a wrong answer. It's obviously not. And you're going to see that even if you thought it was boring in the past, you're going to find out that statistics is actually one of the most interesting subfields of math that there is. Right? It just gets a bad name because people do it in a really boring way, but that's not going to happen here. Okay. Instead, look at things in a framework that simplifies sort of everything we're doing and is going to allow us to build the tools to become really good statisticians. So, what framework is that? That framework is the framework of a random variable. When we understand what a random variable is, then probability and statistics just become two ways to look at random variables. Given that, next question is, what's a random variable? We call the variable quantity x. In elementary algebra, we learned that a variable was something that has unknown value. It has fixed value, but you don't know what it is. Find the random variable is to extend the definition of a variable from algebra and say a random variable is a quantity that's both uncertain and unstable, right? It can be more than one value at any certain time. But really, I think that does us an injustice to not examine a little bit more deeply the word random, right? So what does random really mean in this context? To answer that, we have to ask ourselves, of course, what does random mean? So, today, the word random is used to mean many things, including an outsider, right? So we could say, I saw some random guy on the subway. What does that mean? That just means someone I don't know, right? I could also use it to say something's unplanned, unpredicted. Like, it's so random that I ran into this person at the mall. Again, that word so is also strange because pretty recently we've started to refer to the word random as a continuous quantity, which doesn't really make sense. And even more strange is we don't really hear about more and less random. We only hear about so random and totally random. So that's confusing. So we contrast that to the formal definition, and we can read that it's without definite aim, direction, or method. And we realize, well, that's not that much better for what we're trying to do because there's a book called Random Methods, right? So that doesn't make sense either. So to understand this word, maybe we should go back in history. We can see that in the 14th century, random meant fast, meant to run fast, right? You could say run with great random, or you can say run at random, right? And this meant to run fast. And you can see that sort of a natural progression to running really fast and forgetting something, right? So you can see that in over a couple hundred years, the word started to change and started to mean without purpose or with haste or forgetting or unplanned, right? So things we associate with speed. Around 1800, when that definition was in vogue, the concept of the random variable and was formalized as part of probability theory. And what's interesting is that's late, right? 1800s is pretty late for math. And one reason why it took so long was it was very controversial, and this is something that's been controversial throughout the history of science. And that is randomness itself is a controversial idea. So let's explore why. There's long been a debate about the concept of free will and determinism. Right? This is a very old philosophical question. And randomness has entered the conversation because if randomness exists as a real quantity in the universe, then it cannot be deterministic. So it doesn't say much about free will, but it still has a lot to say about this debate, and because of that, it's quite controversial because there's many people who really want to resist the idea of randomness because, frankly, a random universe doesn't seem to have as much purpose. So let's look at some of the biggest hits of randomness through history, right? So on the left, you'll see a collage called Squares Arranged According to the Laws of Chance. And this was a big statement, right? So at the time, it said something important, right? This concept of randomness. The idea is that this collage was made with no purpose, no aim. The squares fell where they may, and chance controlled them. Now, obviously, the reason why there's been pushback against random is you can easily say, of course, that didn't happen, right? The squares maybe fell according to the laws of wind, of a ventilation system, of where you drop them, right? Like if you knew more about the variables, you could predict where the squares would land. And so the next picture you see is Percy Diaconis, famous mathematician, but he's in this slide because he's able to flip a coin, I think a quarter, and have it land heads 10 times in a row. And this is an eccentric idea, but this is to show that a coin is not random, it's just hard to manipulate, right? So randomness is a model for a coin which isn't actually random. However, the next picture that you see, Vazirani is a computer scientist who recently was able to describe something called Einstein's certified randomness. So this is an idea that at the quantum level, randomness is real, and even Einstein would certify it, which is a big deal because Einstein and Bohr had famous debates about this, right? So what's interesting about the idea of randomness at the quantum level is it doesn't say that some events are random and some events are not random, right? It says that all events are random, and things that appear non-random, like flipping a coin and having it land heads 10 times because you know how to flip it, are actually sort of the collapse of so many random variables that you can predict with high probability, but everything's random, right? So it's a big statement for our reality. It's also one that I think even though I would say Bohr's model has definitely been accepted, I would say that this is not a debate that there's true consensus on. However, what's most important is the last picture, the last person you see, and this is George Box, and he famously said, "All models are wrong, but some are useful," and this is certainly true about randomness. So with that in mind, we can begin our study of randomness. Remember that we're studying something that has a lot to say about the reality of our universe, and whether we know what it says or not, it's also very, very useful. Now that we've talked about the history of the random variable, let's talk about the actual rules, right? What is a random variable in probability and statistics, right? So a random variable only has two rules. It's nice, right? One of those happens to be a 3-part rule, but still only has two rules. So, first rule is very easy. It has to come from a probability triple. What's that? Well, you can just remember the month of September. So SEP, S stands for sample space, E stands for event space, and P stands for probability space. The second rule is that a random variable must have outcomes or its support in the reals. All that means is the outcomes of the random variable have to be real values. So for example, if you have a random variable to describe flipping a coin, then you have a 50% chance of either seeing heads or tails. But you can't use heads and tails as outcomes, you have to use real numbers. So we can just map heads to 1 and tails to 0, and we're good. Okay, so there's 3 strategies for the analysis of the random variable. There's the first is analytical, which is in some ways the best. It always gives us, it's always true, it's fast, sometimes it's hard, and sometimes actually impossible, right? If we want to be able to describe our random variables analytically. The second strategy is we can enumerate them, right? So this can be very, very slow, still always true, but sometimes even impossibly slow, right? The last way is the fastest way, in some ways the easiest way, is we can simulate from a random variable, right? So we have lots of techniques. This is what we're referring to when we talk about random methods, right? So we're sampling somehow, or we're trying to approximate randomness to learn something about a distribution. Now, that usually doesn't give you the exact truth, but it's often the only way we can, right? So we're going to consider all three of these different methods, and we're going to start now by considering both enumeration and simulation for the two random variables that we just talked about. Okay, so let's consider the code we all have shared, right? So let's look at each block of code. So this block of code is used to acquire the sample space and the event space and the support for a random variable that's based on the roll of a single die. So the first function returns us the sum of any amount of dice with any amount of sides. The second function, what it does is, depending on whether we're interested in the sign or the value, it repeats the first function many times and then gives us back a list that has all of the events, right? So this gives us events. So this block of code is used to enumerate the outcomes of one or more dice being thrown. So this block of code allows us to calculate the probability space based on either a list of simulated events or enumerated events, right? So for either one, the probability of that event is the number of times it occurs over the total. Finally, we have a little block code we use just to plot our results and to print our result. First, we run the code for the discrete uniform random variable. So we set our names and our settings to give us, a discrete uniform random variable. So that's a single die with 6 sides, and the rule is to look at the value, right? And what you see here is that there's a difference, right, between the simulation and the enumeration, right? So the enumeration, all the bars are the same height, right? Because that's the real probability. In the simulation, they're slightly different, right? So you can do more and more trials, and they'll get closer to reality. But again, it's a simulation, right? So this approximates the random variable, which is fine. Notice here you have the PDF, right? The probability distribution function, and the CDF. If you aren't sure about this, the CDF is the cumulative distribution function. All that means is it's giving us the probability that the random variable returns a number less than or equal to that number, right? So there's a difference between saying what's the probability that a single die will be 6, that's 1 over 6, and what's the probability that the value on a single die will be 3 or less, so that's half, right? So that's the probability versus the cumulative distribution. Newly, random variable, same idea. You see that there's a 50% chance of seeing 0 or 1. In this case, you see the simulation looks quite like the enumeration. Little aside, right? We run our same code as the first example, the discrete uniform random variable, but we add one more die. So now it's the sum of the values on 2 dice. And we notice a few things. The first thing we notice is this isn't famous. There's no name to go for this random variable. In the future, we're going to learn about exactly why that is. We also notice that the distribution is no longer uniform, right? There's no longer equal probability. And you probably remember, growing up, throwing dice. If you ever were gambling, you probably learned that 6 happens a lot more than 1 or 12, right? And that's because there's more ways to make 6 than there's to make 1 or 12, and that's what these plots show. And let's formalize them and talk a little bit in detail about these two random variables. So first, we had the discrete uniform random variable. We haven't used this word yet, but when we talk about random variables, we talk about the parameters, right? So the parameters are just the values that can change about a random variable. So in this case, we did say the die had 6 sides, right? So the parameters of this random variable are the amount of values that it's allowed to take, right? So it's usually described as a range. So in our case, to formally describe this, we would say 1 through 6, and then the other parameter that's often used is n, but n can be inferred, right? So if the numbers are 1 through 6, n is just 6. You could have a die, right, that has values from 5 to 15, and then n would be 10, right? So we were able to calculate the probability distribution function and the cumulative distribution function. We know what those are now. We didn't talk about the mean or the expectation or the variance, but we're going to leave that as homework, right? So we can change our code to calculate that. So for each of the random variables, we want to think about a problem that we can assign them to, right? So the problem that we're going to keep in mind when we think about this random variable is called the German tank problem. So historical setting, it's World War II, and the Germans are building tanks. And the Germans are very organized and very detailed, and they give every tank a number. So the first tank that they make is tank number 1, and then tank number 2, and tank number 3, and so forth. And the Allies, or the Americans, I'm not actually sure, I think I've read it as the Americans, they want to know, of course, how many tanks have the Germans built. They have no idea. All they know is the Germans build tanks each month. They don't know if it's 1 or 10 or 100. However, they get some spy work, right? So let's imagine that they're able to get some pictures of German tanks, and let's also just imagine that they can get them randomly, right? So there's no bias to how they receive these pictures. They're just getting pictures of tanks. So let's say they see 4 pictures, right? And the 4 pictures show tank number 1, tank number 15, tank number 30, and tank number 45. The question is, given that those 4 numbers are out there, how many tanks do the Germans have? So we know at least 45 tanks, right? Because that 45th tank is there, but maybe not 1,000 tanks, because the probability of seeing only up to serial number 45, given that there's 1,000, is probably pretty low, right? So what we want to say is, what's our best guess? So we're going to solve this problem. It's not super trivial, but it's something that we can think about for now, and we're going to consider the 2 cases, right? So that first case, and also we can consider the case where the numbers observed are 1, 2, 4, and 46. One thing then to immediately ask is, okay, in that case, we know there's at least 46 tanks, but the other numbers are quite small. Is our highest probability guess higher or lower than the first case? So with that in mind, we're going to go on to the next random variable. Newly random variables, the parameters, there's really only one, right? Just P, probability of success. So in our example, the sign of the die is, whether it's even or odd, is equal probability, so P is 0.5. The inferred parameter is Q, which is just 1 minus P, right? We calculated again the PDF, the CDF. We didn't calculate the mean or the expectation, but those are in the homework. And we are going to talk about one historical problem that it's a fun example, and we're going to think about this, and we're going to try and associate this with our Bernoulli random variable. And so the problem goes like this. Imagine that Fermat and Pascal are playing a game. And it's a game where they gamble, right? So they each throw down some amount of money, maybe they each put in like $100. And then they play a game of chance of chance and skill, and they play, for example, 7 games, and it's the first person to win 4 games wins, right? So we would call that, best 4 out of 7, 7-game series, etc. Now imagine they're playing and the series is interrupted after the first game, and Fermat wins the first game, but they can't finish for some reason, so he demands all the money. He demands all $200 because he says, I won a game and you didn't win any. And of course, that's not fair because Pascal still could have won the series. So the question is, can you think of a fair way to divide the money, right? And what fair here means is, can you divide the money fairly based on who you think would have won the series based on the results of the games played so far? So intuitively, we can think that if Fermat had won 3 games and that Pascal had won none, the probability that he was going to win the series is much, much higher, right, than if he had, say, won 2 games and Pascal had won 1. Right? So let's keep that in mind, and let's now we're going to consider what happens when we add random variables. So now we're going to consider, just like we did for the discrete uniform, we're going to consider what happens if we add Bernoulli random variables. We are going to redefine success. It's no longer going to be even or odd. Now it's going to be a value greater than 4. So only 5 and 6 are success. Given that, we have a 1 in 3 probability of success. So we can look at our our sample space is now a little bit more complex. Our event space is now includes the 4 events. You can either have 0, 1, 2, 3 successes. And our probability space is no longer uniform, just like in the other example. It now has a peak. Of course, this is a famous random variable, and this is called the binomial distributed random variable. So this time, instead of going right to the computer to enumerate and simulate, we're actually going to try to solve it analytically first. So let's see if we can figure out the probability distribution function analytically. So to do that, we're going to move to the whiteboard. Here we go. We want to calculate the probability density function. We're just going to write a couple cases right here just to refresh us. This is success, success, success. This is success, success, failure. And we know that the probability of this one is P, which P times P times P, and the probability of these ones are all the same. Its probability is P times Q, right? Because the order of P and Q don't matter. So it's P squared Q. But we also know that we have to multiply it by 3 because it occurs 3 times. So now we want to figure out how to calculate our distribution function in general. So we're going to say, okay, probability that big K equals K. Well, we know that if we know what P is, which we have to, and we know what N is, right? So N is the number of the trials in the Bernoulli, the number of Bernoulli trials. Then we can calculate this first part, right? So we can say, well, that's going to be P to the K times Q to the N minus K, right? Just like we're seeing here. So we have 2 successes, right? And we have P squared times Q because there's 3 total trials. But then we know that there's this other term here, which is how many ways. And that term is standing for the fact that there's 3 different ways to have 2 successes and 1 failure. You may remember that there's a way to calculate this a little bit better. So if you have n trials and you want to know the probability of k successes, you can think of that as drawing your trials. Let's just draw 5, for example. So you have trials, and then you have successes. You have k successes. So if k is 5, there's only one way for that to occur. You have to succeed every time. If k is 0, there's only one way for that to occur. You have to fail every time. But if k is, for example, 4, or if k is 1, it's a little bit. So if k is 1, we could either put the success here, 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 or here. Right? So there's 5 different ways. So if you guys recall, this type of arrangement is called a choosing operation, right? So it's called a combination. So we refer to this as n choose k, or 5 choose 3, right? So what it's saying is how many ways can you choose 3 spots out of 5, right? So in this case we chose 1 spot out of 5. So choosing 1 spot out of 5 is drawn like this. It's 5 choose 1, and it is 5. If you recall, 5 choose 2 looks like this. And if we don't understand why we can talk about that in class. So this is how we represent the number of ways. Wrapping that all up, we now have our probability distribution function, where probability that k equals k equals p to the k q to the n minus k times n choose k. Okay. And of course, we can do the same thing. We can simulate this using our code. We do have to hack it a little bit. We're not going to get into those details, but you can see that we changed our code slightly to allow it to give us the result for a combination of Bernoulli's, and when you do that, you get the following distribution, and we can verify that this is the same as our analytical prediction. So to recap, that is of course the binomial random variable. Remember, the parameters are p and n, right? So n is the number of Bernoulli trials, right? And the p is your success probability. Of course, q is 1 minus your success probability. We know explicitly our probability mass function because we calculated that by hand, right? We haven't talked about the mean or the expectation. We're going to leave those for the homework. We haven't talked about the variance either. That's also going to be done in the homework. We're actually going to think of a very relevant current problem, right? So we're going to think about how we could model gene expression with a binomial random variable. So and to think about that, let's imagine that we're doing targeted sequencing on 3 genes that are equally expressed. So that means that if we sequence 100 reads, then each of these reads, on average, gets 33 of the reads, right? So 1/3 of the sequencing. So we can imagine that if we do this, and we do this under different conditions, it may change. So what we can ask is, given that the gene has a success rate, right, of 1/3, and we sequence 100 reads, so can we give a confidence interval for how many reads we expect to see? And if we do that, then can we declare an observation of, say, 60 reads or 1 read as strange or statistically significant? So that's our last problem to sort of apply to a probability distribution. We're actually going to learn, we're going to continue that example as class goes on. That's going to get a lot more interesting. So now we're done with our random variables. So to recap, what have we done? We've defined the random variable. That's huge. We understand both the support and the probability triplet, right? SCP, we're not going to forget that. We know that we can create new random variables by adding random variables, but we have to be careful because they can be completely different. We also know how to write code to plot the distribution function and analyze a random variable. We know the 3 ways with which to do it. We've now been introduced to 3 famous random variables: the discrete uniform, the Bernoulli, and the binomial. We've also been introduced to one that's not famous, but we've seen what happens when we add 2 uniform random variables. We get a new random variable that's not uniform. So for homework, we're going to think about the mean, what it means, which is a good reason why we're going to call it the expectation. We're also going to try to calculate the expectation and the variance, if possible, for all the random variables that we've talked about. We will also consider this problem. What if we flip a coin 4 times and we define a random variable to represent the number of heads that occur consecutively? Can you make a random variable to model this process? Lastly, our homework is to think of a process in your research that can be described by a random variable.